This is a short video about Big O notation. Big O allows us to express or represent the efficiency of an algorithm. So we can use Big O to see when one algorithm is more efficient than another algorithm. So here is a graph showing some common Big O runtimes. On the left axis, that is to say the y-axis of our graph here, we have runtime, which is how long the program or algorithm takes to run. On the x-axis, we have n, which we call problem size. You can also think of it as the size of the input or the size of the data that the program is operating on. For example, for a search, it would be the number of items that potentially need to be searched to look for the item that we're looking for. So the simplest Big O to talk about is Big O of n. This is when the runtime of the program is directly proportional to the number of items. So for example, for linear search, we have to examine every single item to see if it is the item we're looking for, and so that takes Big O of n. So as the number of data items increases, the runtime increases proportionally. Some other common runtimes are O of n squared, where the runtime is the square of the input size. Many common algorithms are this. For example, some of the common sort algorithms that you might have heard of, like bubble sort, require O n squared. Another common runtime is O log n. What that means is that the runtime is the logarithm of the input size. And this is true for binary search, and we'll talk more about that in a moment. One more runtime that's highly desirable, although rarely achieved, is what's called Big O of 1. What this means is that the runtime is constant. As the size of the data set increases, the time required to run does not increase at all. And this can be achieved in certain cases. For example, when looking up an item using hashing, we can frequently achieve a constant runtime or Big O of 1 runtime. So to illustrate this, I want to talk about binary search versus linear search. So linear search, we said, takes Big O of n. So if we search 1,000,000 items, then with linear search, then we have to check each of the 1,000,000 items. And if we check 1,000,000,000 items, then it takes 1,000 times longer. We have to check each of the 1,000,000,000 items. For another good search, or a better search in when your data is sorted, is binary search. Binary search is much more efficient. It only requires the logarithm of the number of data items for the runtime. So whereas linear search for 1,000,000 items requires a runtime of 1,000,000, for binary search, if we have an n of 1,000,000 items, the runtime is approximately 20, the log base 2 of the number of items. So we can see then that binary search is much, much faster as n grows larger. And indeed, that's what Big O is about, is how the runtime changes as a function of the input size, and when that becomes just blindingly obvious is when we have a large input size, which is what could conceivably cause a program to run slowly, and so that's the case that we care about. So again, Big O notation is a concise way to express the runtime of an algorithm, and these curves up here are some of the common runtimes. The book has a more complete chart, but these are the most common ones.